In this video, we're going to talk about the exponential distribution. The exponential distribution is for the random variable x, which is going to be the amount of time between two consecutive events. It's, for example, if you're staying in a bus station, the time between the two buses is going to be the random variable, and the distribution, the exponential distribution, is going to model that random variable. So it's coming with this density function f of x, which is going to be 1 over lambda e in the power of minus x over lambda, where lambda is going to be the average waiting time. What does it mean? It means that if you stay in a bus station for 1 hour, and if you see there are 5 buses came to the bus station, so you can guess that in average there are the average waiting time between the two buses is equal to the 12 minutes. This is what does it mean, this lambda. So in this video lecture, we're going to talk about the basically 3 things. The first one is going to be the cumulative distribution function for this random variable. The second one is going to be what's the expected value of this random variable. And the third one is going to be what's the variance of this random variable. So let's start with the first one. The first one is we need to figure out what's going to be the cumulative distribution function. So if you remember the definition of the cumulative distribution function, it's the probability that your random variable is smaller than this value a. So by the definition of how, so usually we find the probabilities by integrating the density function. So from 0 to the a in this case. So this starts from the 0, not from minus infinity, because x, which is the waiting time, can be negative. So I'm going to substitute the density function to here. It's going to be the integration from 0 to the a of the density function, which is 1 over lambda e in the power of minus x over lambda dx. So the antiderivative of the second term is going to be minus lambda multiplied to the e in the power of minus x over lambda. So we have to evaluate this at the 0 and a. So please note that this lambda and 1 over lambda are going to cancel each other. It's going to be e minus e in the power of minus x over lambda, and we have to evaluate this at the 0 and a. So if I substitute the a, it's going to be minus e in the power of minus a over lambda, and if I substitute the 0, it's going to be plus e in the power of 0, which is 1. So the answer is 1 minus e in the power of minus a over lambda. So we've got a formula for the cumulative distribution function. It's going to be f of a is equal to the 1 minus e in the power of minus a over lambda. So what does it mean? It means that if I know that in average the buses, so the time between the two consecutive buses is equal to the 12 minutes, and if I would like to know what's the probability that I'm going to wait less than 12 minutes, right? So what's the probability that I'm going to wait less than 12 minutes for the next bus? It's going to be the cumulative distribution on top 12. And I just need to substitute everything to this formula. It's going to be a 1 minus e in the power of minus 12 divided to the lambda. In this case, it's also 12. It's going to be 1 minus e to the power of minus 1. So let's do the second part. So the second property. So the second property, we have to evaluate the expected value. So do you remember what's the meaning of the expected value? So the expected value means what's the average of this x. So actually, if x is the waiting time, which has the exponential distribution, which is coming with the parameter lambda, which is actually the average waiting time, right? So the expected value of the x should be equal to the lambda. But if you don't believe me, we can try to prove this. So let's try. So the expected value, by the definition, it's going to be the integration of the x multiplied to the f of x from minus infinity to the plus infinity dx. So I'm going to substitute the density function of this x. It's going to be integration from minus infinity to the plus infinity. Oh, so let's wait here. So x multiplied to the 1 over lambda e in the power of minus x over lambda dx. So I have to integrate this from 0 to infinity, because again the x, which is the waiting time, can be a negative. So now, so this is slightly different as before. So before the integration was very simple because I didn't have this x. So now we have this x, so that's why we have to use so-called integration by parts method in order to integrate this. So we are going to basically denote the u as the x dv. It's going to be a 1 over lambda e in the power of minus x over lambda dx. Then du is going to be equal to the dx, and v is going to be equal to the antiderivative of this term, which is going to be minus e in the power of minus, oh, let me write this. So 1 over lambda multiplied to the minus lambda multiplied to the e in the power of minus x over lambda, which is going to be equal simply to the minus e in the power of minus x over lambda. So according to the formula of the integration by parts, we have to multiply u to the v first of all, then v to the du. So this is going to be x multiplied to the e in the power of minus x over lambda was the minus, and we have to evaluate this at the 0 in infinity, plus the integration of, so this term multiplied to the dx. So e in the power of minus x over lambda dx. So please note that it should be minus here, but this minus is going to be canceled with this one, and it's becoming plus. So let's look to the first term in more detail. So I would like to evaluate this one. So x e in the power of minus x over lambda. I would like to look to this in more detail. So I have to evaluate this at the 0 in infinity. So if you just split the 0, it's going to be simply 0, right? It's super clear, because this is going to be minus 0 multiplied to the e in the power of minus 0 over lambda. So this term is equal to the 1, because e in any power, so anything in power 0 is 1, and it's multiplied to the 0. It's going to give you a 0 plus. So if I can't really put the infinity instead of x, so we have to find this using the limits. So the limit of x, so I'm going to multiply to the e in the power of minus x over lambda as the divided to the e in the power of x over lambda. So instead of minus, I'm going to make it plus. So we have to evaluate this when x goes to the infinity. So you know that the exponential function is reaching the infinity much faster than any linear function. So that's why it's obviously going to be in the form of 1 over infinity, which is equal to the 0. But you can do this using so-called L'Hopital's rule as well. So the L'Hopital's rule tells you that this limit is equal to the derivative of the both of the parts of this fraction. So basically, I have to take the derivative of the x with respect to the x, which is going to be equal to the 1, and divide this to the derivative of the e in the power of x over lambda, which is going to be e in the power of x over lambda multiplied to the 1 over lambda, right? So now it is equal to the 1 over infinity, which is equal to the 0, right? Because if you substitute the infinity instead of x here, you're going to get the infinity in the denominator. So basically, what we have just shown that this is equal to the 0. So what I'm interested is, so we need to evaluate the second term actually here. So the second term is going to be, so we have to still evaluate this from 0 to infinity. So the antiderivative of this term is going to be minus lambda e in the power of minus x over lambda, and we have to evaluate this at the 0 and infinity. So if you evaluate this at the infinity, it's going to be simply 0. So because it's lambda e in the power of minus infinity over lambda, so e in the power of minus infinity is equal to the 0 plus lambda e in the power of minus 0. So this term is going to be equal to the 1. So that's why the answer is equal to the lambda. So we've just shown that the average waiting time is equal to the lambda but please note that we knew this before, right? So it's a definition of the lambda. So let's try to do the third part, the last part of our lecture. So we're going to try to calculate the variance of the x. And we're going to do this using this formula, the expected value of the x squared minus the expected value of the x in the square. So we know that the expected value of the x already, so we just need to calculate the expected value of the x squared. So we are going to do this in a very much similar way as we did before. So the expected value of the x squared is going to be equal to the integration of the x squared multiplied to the density function. So in this case, it's going to be from 0 to the infinity. Again, it starts from the 0 because x can be negative. So it's going to be integration from 0 to the infinity. So the x squared multiplied to the density function, which is 1 over lambda e in a power of minus x over lambda. So which is slightly different as before than before. So before we used to have just x here. So now we're going to have x squared. So what does it mean? It means for us that we have to do the integration by parts twice. So one time we're going to do this instead of get rid of this x squared. So we obviously are going to have the x, and then we're going to do this second time. So so everything is more or less like technically everything is more or less straightforward. So u is going to be equal to the x squared, dv is going to be equal to the 1 over lambda e in the power of minus x over lambda dx. Du is going to be equal to the d2x dx. V is going to be equal to the minus e in the power of minus x over lambda. So we have to multiply u to the v, then integrate v to the du. So it's going to be x squared was the minus e in the power of minus x over lambda from 0 to the infinity. So we've seen before that whenever it was just simply x, it was 0, right? So now whenever it's x squared, it's also going to be 0. So this overall term is going to be 0. Because if we substitute the 0, so it's going to be a 0 multiplied to the 1, which is equal to the 0. If we substitute the infinity, it's going to be, so infinity over infinity, actually, but the exponential function grows faster than the linear any power function, actually. So it's going to be simply equal to the 1 over infinity, which is equal to the 0 again. So the second term is going to be, it was a plus now, so plus the integration of 2x e in the power of minus x over lambda dx. So which is very much similar to the x multiplied to the e in the power of minus x over lambda, right? Isn't it? So we have to integrate this from 0 to the infinity. So if it would be, so I just need to integrate this one, but please note that this is very much similar to this one, right? So if it would be in the form of, so let me write this. So the integration of from 0 to the infinity, 1 over x multiplied is a 1 over lambda e in the power of minus x over lambda dx, then this would be exactly the definition of the e of x, right? So what I have to make, so what I have to do with this in order to bring this, right? So I have to still multiply this to the lambda, and I have still multiply this to the t. So if I multiply 2 lambda to this integration, I'm going to have exactly this one. So this is e of x, which is equal to the lambda. We've just calculate this. It's going to be lambda multiplied to the t multiplied to the lambda, or 2 lambda squared, actually. So we know now what's the e of x squared. So it's going to be 2 lambda squared minus e of x is also lambda. So in the square, it's going to be squared. So this is going to be lambda squared. So in this video lecture, we have obtained 3 formulas for the f of a, which is going to be 1 minus e in the power of minus a over x. We've got the formula for this one, which is going to be equal to the lambda, and we've got a formula for the variance, which is equal to the lambda in the square.